page. Thanks everyone for coming to this, the latest edition of our camera expert seminar series. So what we're doing is every 3 months we invite someone down who's an expert in their area and related to the research we do in camera. And afterwards you can stay around and have a drink and talk to Will. So speaker today is Dr. Will Smith from the University of York, and Will is an expert in computer vision. He's in the computer vision and pattern recognition group at the University of York. I think you graduated in 2007, PhD from York. I've known Will for, I was trying to remember how long I've known Will for now, and I can't remember, over 7, 8 years from the EPSC workshop.
10 years.
10 years. 2009. EPSC Sandpit workshop, which we went to, and actually managed to get some money, kind of, out of it. There's a grant funded, which is good stuff. Yeah. And also kind of known Will through my research area. It still is a bit sort of on kind of faces and facial analysis, my personal interest, and Will has published a lot of excellent work on facial analysis and facial sort of capture. But Will has also kind of expanded beyond that now. And I just asked Will, I was looking forward to a face talk. He said, there's actually going to be a little bit of faces in this one. So looking forward to kind of seeing what we can hear about. But I'll leave you with Will and enjoy the talk.
Okay. Thanks very much for the introduction and also for the invite. It's really nice to have an excuse to do that. I feel kind of not worthy of being called an expert somehow, but anyway. So, with a talk like this, it is a little bit difficult to know kind of how to pitch it because I know it's quite a broad audience. But on the other hand, I want to tell you something about the detail of some recent work. So I've tried to kind of do both, and probably in the end will satisfy no one. The theme is what can vision and graphics learn from physics? What I mean by learn here is in the machine learning sense. And this talk is covering something, a kind of theme that I've been trying to follow for the last couple of years, to try to bring together the amazing improvements that machine learning has brought in computer vision, but with also some principal modeling of what we do actually know about the visual world and the physical world. So in this talk, I'm going to concentrate on two pieces of recent work where we're blending some kind of physics-based model with machine learning. And along the way, I'll try and give some arguments for why I think that's a good idea. So, okay, I'm going to start by describing a couple of my favorite problems that I'm interested in. So one is inverse rendering, the other is nonlinear statistical shape modeling. I think both are kind of some interest to people here at the science department, camera, people working in vision and graphics. Then I'm going to kind of go on a slight tangent to argue that supervised learning is not going to solve all the problems that we have in computer vision. And in particular, the data we have and will need to solve all of the problems in a supervised fashion doesn't exist and maybe couldn't ever exist. Then I'm going to go into two pieces of recent work tackling the problems that I've described. The first is using something, what I would call self-supervision to tackle the inverse rendering problem. And then I'm going to show how you can blend a physical deformation model into learning a nonlinear statistical shape model. Okay, so that's what I'm going to cover. So let me start first by introducing what I think are two interesting problems. So, we have an image of a face, and I would like to be able to explain why that face appears the way it does. Or in fact, I would like to be able to explain why any image appears the way it does. When I say explain, I mean in a physical sense. So what are the physical properties and processes that underlie that image appearing the way it does? And you can kind of think about this problem at a few different levels. So maybe as a first step, you could think of decomposing this image into two terms. So a shading term, which is related to the geometry of the shape and also the illumination environment. And then the kind of intrinsic reflectivity of the surface. So informally, we might call this the color of the surface or the texture. Being more precise, we should be calling it the albedo. So these two things multiplied together give me this image. And this kind of first level of decomposing appearance is called intrinsic image decomposition. See, if you're a non-vision person, like we think this is an interesting problem in and of itself, but you may say, well, what's the point of that? There are some reasons for wanting to do this. So this map is an invariant property of the scene or the object. So if you want to recognize the object, if you can extract this information, then you would be invariant to illumination variation. So this is a challenging problem in view vision. There are other applications. For example, it might be useful for editing. So if, say, someone's got some freckles and you want to remove them or you want to add some freckles, if you add them in the albedo map and then blend it back together with the shading, you should get a kind of plausible appearance. So there's useful applications for just being able to do this. But we still don't really have a full explanation for why the image looks at it as it does. So let's go one level deeper. You might choose to separate the reflected light into the light that bounces straight off the surface. So this light does not take on the color of the skin, and it also captures the very high frequency, high detail appearance of the face because it's reflecting off the outside, so things like skin pores and wrinkles are visible. And you might separate that from the subsurface light. So here we've got the diffuse shading. So this is still a property of geometry and lighting. The difference now is that this light has actually penetrated the skin and been diffused. So you probably can't see on the slide, but this shading is much smoother than this specular shading. And some of the light has been absorbed by the pigments in the skin, and that's captured in this albedo map. Okay, so we've gone kind of one level deeper. We've now separated surface reflectance from subsurface reflectance. But we could go even further, and now I think we're approaching like a full physical explanation of why this image looks how it does. We could also try to separate the shading into the underlying geometry and then the lighting that the face was captured under. So, in my view, this now gives us a full physical explanation of why this image looks like this. And now, hopefully, you can see there are loads of applications. If we could really solve this inverse problem, well, this is object capture, 3D scanning. So if we could do this really well, we could use this for avatar creation. We can maybe do recognition on the 3D shape. We might animate it with new expressions and so on. And I spent my PhD working on the rather optimistic problem of trying to go directly from this image to the geometry. So this is a classical problem in computer vision called shape and shading, and it's attracted a lot of work, and it's a very interesting problem mathematically, but has not really proven that useful in a practical setting yet. So let me show you where I started with my PhD and where I finished with my PhD, and we're later going to come back and see that maybe it is just about doable. Okay, so in my PhD I was working with images like this, and if I took the state-of-the-art shape and shading algorithm 2003 when I started, I was getting models that looked like this. So, pretty horrendous. I spent my PhD trying to kind of blend this with learned statistical models, so actually somewhat similar to the theme of the talk today. And by 2007, I could get models like this. And you may say that looks okay. It does look okay. It's not accurate at all, but it sort of looks conceptually okay. But I should add some provisos. So first of all, it only works for faces. This is using a statistical model of face shape in a frontal pose with tons of assumptions. So the camera has to have linear response. I'm assuming there's a single point light source in the scene with a known direction. I'm assuming the image is being aligned to my model perfectly. I'm actually ignoring the albedos and the texture completely in this reconstruction. So that was as far as I got really with shape and shading, and it's a very difficult problem, and I kind of gave up on it for a period. I'm going to come back to this later in the talk and show you with deep learning and with some modelling, you can do much better and you can get rid of a lot of those assumptions. my second, I would say, interesting problem. So this is really in a completely different direction, but I'll try to pull them together. So the second area I'm interested in is learning the variability in an object class. So for example, faces. So actually I've just realised, I said to Darren this talk's not about faces, but it's all been faces so far, but it won't be in a minute. Okay, so statistical shape models are essentially learned manifolds of the principal variations that you see in a set of shapes from an object class, so for example faces. So in a classical PCA model, what you get is an average 3D shape, and then these linear modes of variation, each of which are the axes of some low-dimensional subspace. And the idea is that these axes span most of the variation in your data set. So this is the single most important linear variation in face shape. For those of you working in camera, you might want to think of these in terms of blend shapes. So these are basically the same idea as blend shapes, the difference being that these are orthogonal and also they don't have any semantic meaning, so they're just learned from the data. So why would you want a statistical model? Well, the idea is that a problem like I just showed you, recovering the shape of a face from a single image, becomes much easier if you constrain yourself to this linear subspace, so this learned much lower dimensional space. So the original paper in 1999 from Van der Vesser used really amazing results. They learned the model from a set of faces. They could take a 2D input image, find the best model fitting parameters to explain that image, get the reconstruction. Then they could do things like edit the expression or some other semantically meaningful parameters and synthesize new images. Here's another nice application, editing the expression in photographs. So what would the girl with the pearl earring look like if her mouth was open or closed? More recently, this is some work on estimating naked body shape from clothed scans. So if you want to buy something off Amazon without trying it on, you're not willing to send like naked selfies to Amazon, then this is a good way of doing it. So, okay, statistical shape models are really useful, and they've been around now for, at least 3D dense statistical models have been around about 20 years. They're primarily still linear models, and I think this is a really major limitation. So loads of the interesting shape variation that we see in the world is nonlinear. So this image should serve as a warning to any PhD students considering working in industry. If you go and work for Disney, you risk being slapped across the face in the name of science. But look at this really interesting soft tissue dynamics when you do slap a face, and like the recoil you get in the cheek. There's loads of other examples, so things like articulations of joints are nonlinear, flapping, bending, stretching, things like gaining and losing weight in an individual. To take a classic object from 3D computer graphics, so the Tosca cat, like the variation here is clearly nonlinear in loads of different forms. So there's articulations of the leg, bending of the tail, bending of the whole body. Being able to model this is really important. Another kind of challenge is that, and this is going to link back to this, the kind of relationship to learning later on, is that actually 3D data is really sparse compared to what we've got available in the form of 2D images and videos. So a typical 3D database is going to have on the order of hundreds, maybe thousands of shapes. Okay, there's things like ShapeNet, which are maybe larger than that. But if you decided you wanted to go and build a model of cats or something, acquiring more than thousands of 3D cat models would be a really big challenge. However, the resolution of this data, especially if you want to capture really high quality, fine 3D shape detail, could be up to the order of millions of vertices. So we've got a high dimensional space that's sampled quite sparsely, and I think what we would want our model to do is somehow interpolate between these sparse samples in a physically sound way. so that the object appears to be physically plausible. Okay, and the last sort of challenge I'd like to pose in this area is that when we capture these shapes and we capture a deforming object, we're actually measuring two things. We're measuring the interesting deformation of the shape, but that's superposed on top of some rigid body motion that is probably not interesting, or at least we probably want to model it separately. So to give you an example that I think is quite relevant, camera. So this is basically someone building a rig, so they're requiring 3D scans of some different posed static expressions. And what you can see is that, so to take this example of the jaw opening, if you build a blend shape from the neutral and the jaw opening, you can see that the top of the head raises. So every time you open the mouth, you would also raise the top of the head. So the challenge is, how do you separate those two things so that you have a statistical model that's completely invariant to these rigid body motions, and then you can kind of apply whatever rigid body motion you want afterwards. So I just want to say something about the classical pipeline for building these models, to kind of point out where I think the flaw is and why this is quite important. So the pipeline is the same in 2D or 3D, and typically what we start by doing is defining correspondence between our shapes. So it could just be some sparse landmark points. It could be a dense mesh template where every vertex is treated like a landmark. Then we do some alignment. So we've got this sample of, in this case, face shapes. And what's done in a typical pipeline is that you somehow factor out rigid body motion. So in this case, they've done something called Procrustes alignment. So they've tried to find the rigid transformation that minimizes the sum of the squares of all the distances between corresponding vertices. So that sounds like a reasonable thing to do, and it's true that this aligned data is now invariant to rigid body motion. And then what you do is some statistical analysis of this data, and that gives you your statistical model. My argument is, why is Procrustes analysis the right choice of alignment for this data? And if you used a different alignment, you would get a different model. So this is somehow theoretically unsatisfactory. The model is not kind of intrinsic to the data, it's also dependent on how you chose to align the data. And to kind of show you some more motivating examples, here I took a face and I edited it by only increasing the size of the nose. The rest of the face is exactly as it was. So the question is, if you wanted to understand the variability between these two faces and you didn't know anything about them, if you were to do Procrustes alignment, the fact that you've stretched the nose out, when you align the two, in trying to align the noses, it would misalign all of the rest of the face. So what's being shown here, maybe it's not so clear, is the variance at each vertex, and there's now variance everywhere. If somehow you knew that the only thing that varies is the nose, and you only align the face and you ignore the nose, then you would only see variance in the nose region. So you might argue that's the more meaningful alignment. But that's only because we knew I'd only edited the nose. If I just gave you two arbitrary expressions, what would be the right alignment between them? And to maybe take a more realistic and challenging example, you've got two human body poses. It's clear that Procrustes alignment between them is not meaningful in any way. And if you think of really extreme poses, it's hard to think of any alignment that would make sense. Okay, so those are the two problems that I'm going to come back to after first trying to argue that we need something more than supervised learning. And I gave a talk at CVMP kind of just over a year ago that was sort of the beginning of me trying to go in this direction. And basically this talk has the results in it that I wished I'd had when I gave that talk. But I'd just like to point out that the big names are finally catching up. So Jan LeCun is kind of now pushing this direction as well. So something like supervised learning is necessary now. Okay, so this is going to be very sort of conceptual and high level. So one approach to classical computer vision, this is not the only one, but a kind of optimization-based approach to computer vision, is that you have some fixed model of a process that you understand well. So that could include like spectral projection, reflectance models, whatever else it is. And you're going to optimize over some parameters that you don't know that you would like to recover, that via this model produce some data, and you have some actual data that you're trying to explain, and you have an objective function that measures how well your estimated data matches your real data, and solve the optimization problem. And all you need is this one data sample, and hopefully you can explain it. So the shape and shading results I showed you earlier were something along these lines. So to kind of give you a conceptual cue that I think this is sort of a good idea or has some value, I'm going to replace the fixed model with pictures of clever people who came up with models that we use in vision and graphics. Okay, so to give you a couple of examples of approaches that would fit into this paradigm, this one actually blends together the two interesting problems I talked about. So this is fitting a statistical face model to an image. So the black boxes are fixed models, so you have this learned shape model, the learned texture model, you have some kind of renderer, and you're optimizing over the red things, so the shape and texture parameters, the pose parameters, and all the environmental parameters like illumination. And so all of these, via this model, these parameters provide this potential explanation of the data, and your loss function measures how well these two things agree. So this is an analysis by synthesis approach. Another really widely used and classical computer vision technique that would fit into this sort of paradigm is multi-view 3D reconstruction. So in this case, your model would be the perspective projection camera model. Your objective function will be measuring the agreement between the reprojections of 3D points into 2D images for points that are known to correspond. Okay, so you can do a lot with just model-based computer vision. But as we know, there's been massive success recently with learning-based computer vision, and in particular supervised learning. So the idea now is you have some input, you have some parametric function, usually a deep neural network, and you have some parameters that you want to learn such that you can directly produce the desired output from the input. By providing a pair of a desired output and the output estimated by your network to a loss function, you can measure how well your parametric function is doing, and then you can try to learn the parametric function given lots of data. So given lots of pairs of inputs and desired outputs, so long as this whole pipeline from the loss function back to your input is differentiable, then you can use backpropagation, and this is really, really powerful, very successful. Again, there's a perceptual cue that I'm telling you, I think this approach on its own is limited. We're going to replace that by a picture of a black box. So, this is great. If you have enough data, I think most people in computer vision now agree you can solve, I hesitate to say any problem, but almost any problem with this sort of approach. If your parametric function is sufficiently powerful, your data is rich enough, there seems in principle no reason why you couldn't learn this mapping from input to desired output directly. And it's the breakthroughs in this have been really amazing. You will have heard this story loads of times before. So if you can get humans to sit and label road scene images with semantic pixel labels, then you can train a network to do this task really well, and really fast as well. You could get them to label objects and give them a textual description, and you put both the computer vision and the natural language generation all into your model and learn to produce descriptions. Okay, other examples, face parsing, face landmarking. So these tasks where either we have access to the labels already, or it's not too much effort for a human to do them, then this is a really powerful approach. So, my argument for why you might need to do something else is because for some problems, it's either very difficult or impossible to obtain training data and all the annotations to go with them, so the labels. And like, a bit more broadly, and I think this is what Jan McCumb was really talking about, was whether, even if we can, with sufficient effort, get the labels for a particular problem, will this ever really get us to general artificial intelligence? Like, will we ever be able to get the richness of data and annotation that we would need? To be a bit more specific, and in the context of this talk, what if you're trying to solve an inverse problem, which is itself unsolved? So in other words, you just can't get the training data because there is no existing method to get you the labels from the input data. So I'll show you what I mean. So in this situation, you have two choices. You can run your imperfect existing algorithm to give you some training data, but then all you're going to do is learn to replicate the performance of an algorithm you've already got. Option 2 would be to synthesize some data using a model, but then I think the concern is whether this synthesized data is realistic enough and diverse enough that you'll really be able to learn to solve the problem in the wild. So, to take the examples I mentioned so far, let's say we wanted to learn phase shape estimation or phase inverse rendering. Well, you can do it. The images I showed you before came from a light stage, so you require this elaborate setup, but in principle, you could scan thousands and thousands of people, then take them outside and in the wild and photograph them thousands and thousands of times, and probably obtain enough data that you could use this of learning approach. But what if you want to inverse render this scene? It's York Minster, by the way. So I mean, what's complicated about this? Well, mainly it's outdoors, so we have no control over the environment. It's also dynamic. There are people in it, so if we need like multiple observations, it's going to be very challenging to capture. So I would say that there is no method at the moment to give us ground truth here. If I want to 3D scan and inverse render York Minster, I don't know of any sufficiently good technique to do this. So then where do I get the labels to do supervised learning? OK, so I think a partial answer might come from self-supervision. I'm going to show you some recent work that I think goes towards solving this problem. So the idea of self-supervision is to put together the two components that I've shown you so far. I should argue that, should explain, this term self-supervision is being used quite broadly at the moment, and it means different things to different people. So this is only one perspective on self-supervision. The idea is you have some input data, and you want to train your black box to transform this data to a useful representation. So in the context of inverse rendering, this would be like a 3D model, the diffuse albedo map, and the lighting, something like that. To train this network, for which we have no labels, you can then include in your network this maybe physics-based model that captures all of the information you know about the forward process. So how you can go from this representation back to predicted output. So the black box is trying to learn to directly solve the inverse problem. The black box is a forward simulation. Sorry, not black box. Clever box is a forward simulation of the process that we do understand and that we can simulate. And then the way that the black box is going to learn is from a reconstruction loss, so just the difference between these two things. So this error, so long as this model is differentiable, then this error can propagate all the way back to our representation and then provide a supervisory signal to this, whatever it is, deep neural network. So if you do this, there are some other benefits besides the fact that you're potentially learning with no supervision. One is the parameters are interpretable, so that embedding in the middle,
it has semantic meaning, so you can actually understand what that representation means and maybe use it for something else. Also means you can enforce some constraints if you know, so for example, diffuse albedo has to be a positive value, so you can exploit that knowledge when you're learning. It means that the components of your model are reusable. So if you've trained a network to do 3D pose estimation, you can take that network and plug it into some other system where you need pose estimation. So this is quite useful. Also, it gives you some insight into the problem and whether it's going to be solvable or not. So I'll give you an example of that in a moment. So whether there is a unique solution or whether it's ambiguous. So let me get on to the first piece of recent work, which aims to tackle this self-supervised inverse rendering problem. So what we wanted to do was quite challenging. So it's take a single image of any scene in uncontrolled conditions as input, and as output predict some representation of geometry. It happens to be a normal map, but that's not particularly important. The albedo map, so the intrinsic color of the object or scene, and the lighting. So all of this from a single image. So just to kind of, there's a lot underlying this, but I just wanted to kind of, given the theme of the talk, hint that like there's some historical physics behind all this stuff. So the reflectance model we use is very, very simple, and to anyone working in graphics, you'll be amazed that we use something so simple. It's just the Lambertian diffuse model. So this says that if your surface is macroscopically rough, then when light strikes it from any direction, it will be scattered equally in all directions. Okay, so this is what a perfectly matte surface would do. So the interesting thing about that is it doesn't matter where the viewer is situated, they'll still see the same amount of light because it's being scattered equally in all directions. I always thought, is this really a good model? People always said it's a good model for paper. If you look at paper under a microscope, you can see it is a good model. Paper really is macroscopically really rough. I think we should really give Lambert some credit for realizing the relationship in this. He discovered this in 1760, that basically the model of diffuse reflectance. And if you think, he didn't have a camera, obviously. He didn't have a digital camera. He had no way of measuring light at all. In fact, all he had was some candles and like a darkened room. But he was able to come up with this cosine relationship for diffuse reflectance. So I think it's pretty astonishing. So basically, the idea is really simple. The light is being scattered equally in all directions. So the only thing that matters is how much light energy is the surface receiving. That's all that changes how much light you'll see reflected. And what Lambert realized is that if you orient a surface away from the light direction, it will receive less light per unit area than one that's oriented towards it. And the relationship is just that the reflected intensity is the cosine of the angle between the surface normal and the light source. That's it. And that's the reflectance model we use. So here is our network. As in all computer vision papers now, it involves increasingly complicated flowchart diagrams. I've got a much more complicated one in a minute. So we take a single image as input. This thing here is our network that we're training. If you care, it's got a shared encoder. The idea being that you're helping the network learn to disentangle these things by forcing it to learn joint features between the two outputs. Then we have two decoders, one which is going to directly regress an albedo map, another one which is going to directly regress a normal map. We don't need to make it learn to predict lighting, because you can infer lighting. If you've got the input image, the albedo map, and the normal map, you can do a least squares fit to compute. In this case, we use spherical harmonic lighting. So that's kind of removing any redundancy from what the network has to learn. Then we have a differentiable renderer. So these estimates go back into a renderer to produce an image. And then we compute the error between them. And this can propagate all the way back into the network and help the network learn. So this makes it look easy, and it makes it look like that might actually work, but it won't work. So this problem is fundamentally ill-posed. And that that error on its own will not allow you to solve this problem. So just to give you an example of what I mean, if you look at this, you might interpret it as a violin hanging on a door, so like a 3D scene. Of course, you're fooled on two levels. First of all, it's not. It's a painting. It's just a very good painting that looks 3D. But second, of course, you're looking at a projector screen, so it's obviously just flat. It's not a 3D scene. So in other words, there's an ambiguity between whether what you're looking at is just painted on a flat surface versus a shaded 3D object. And actually, there's like an infinity of solutions in between those two things where you explain some things in shape or some in albedo. So to go back to my network, a trivial solution would be just the network could just learn to copy the input image through to the albedo map, make the normal map flat everywhere, just a plane, and then it has a good explanation of this image. It's just a flat surface with that picture painted on it, right? That would be a valid explanation of this image. And that is exactly what it would learn if you trained it only on that. So we need more supervision. So some of this is kind of slightly perceptually inspired. So when you look at this image, hopefully all of you are seeing those as convex hills. Do you agree? And the other ones as concavities. And if you reverse the shading pattern, the effect seems to be reversed. So that interpretation is consistent with an implicit prior that you've got that lighting tends to come from above. So our vision system evolved when we lived outside and lighting generally came from the sun. So this makes sense that we've got this prior. So we can do something similar. We can learn a prior for the sort of lighting that typically occurs in the real world. So natural lighting, well, this sounds like it might be pretty complicated. It's all possible environments you could ever find yourself in. But actually, there's loads of statistical regularity in it. So what we do is we acquire a big data set of environment maps. We project them into the spherical harmonic basis, if that's something you've heard of. And then we do a statistical analysis in that space. And we end up with a statistical model of natural illumination. So it doesn't show up so well on this slide, but this is our average lighting, and the most important variation is this one, which seems to be kind of rotating side to side and overhead light. But one thing to note is in most of these cases, the lighting is predominantly from above, and if it's got a color, it's blue, which makes sense because it would be the sky. OK, so this allows us to constrain lighting somewhat. The bit that really makes it work is multi-view supervision. So this is offline. This is not, our network does not require multiple images inference time. But as an offline process, we collect large collections of images taken under uncontrolled conditions with really highly variable lighting. And we use structure of motion and multi-view stereo to compute a 3D reconstruction of the scene along with all the parameters of the cameras that took those images. And continuing with the theme of giving credit to the people in physics who came up with this stuff, I tried to find where the pinhole camera model originates from. And it seems like the mathematical model for perspective projection has been around about 1,000 years, and I think was first written down in this book of optics. So how do we use this? This is where the diagram gets really complicated, so stick with me. So we get collections of images of a certain scene. So we go on Flickr and we type York Minster and we get 10,000 images. And they're really richly variable, so lots of different lighting conditions. We apply multi-view stereo, and then we find a pair of images that overlap a lot. So they're similar viewpoints, but where the lighting is very different. From multi-view stereo, we get an approximate depth map, and we also get the relative camera pose between these two views. And what that lets us do is cross-project between the two images. So we know that diffuse albedo is an intrinsic property. It doesn't change if you change the lighting. So we can use this to measure whether that is true or not. So we can cross-project one image into the other and see if they agree with each other. Is that clear? OK. There's obviously loads of other tricks going on in priors. And we found that we also need to do this cross-rendering where we mix the albedo from one cross-projected to the other with the shading from the other. And anyway, see the paper for more details. So this kind of works. I couldn't believe this actually worked, having failed so dismally during my PhD to actually make this work. So let me just explain what these images are. Here's 3 input images. No knowledge of the camera or lighting or anything. Then the next 3 are our estimates. So this is the albedo map, the illumination environment represented by rendering a sphere under that lighting. Then this is the normal map that we estimate. Maybe you can't really get an idea of whether that's good or not, so just hang on a sec. This normal map comes from multi-view stereo using like 500 images of the scene. So obviously there's some holes here, which we don't suffer from. Also, if you look closely, maybe you can't see it on the projector, there's way more detail in our reconstruction, because we're able to use all the high-frequency information in the image, which multi-view stereo doesn't do so well at exploiting. This column is just a re-rendering of our estimated shape. So this is the one to look at, really. This is the 3D model that we're estimating from this single image. And on the end is just the implied shading. So if you get rid of the color, this is what we predict the shading is. OK, and obviously, compared to other methods, so this is a state-of-the-art single-image depth prediction network. These are the normals that it estimates for this image. These are our normals. This is a classical optimization-based inverse rendering method, SURFs. This is a state-of-the-art intrinsic image estimation method. So again, if you look at the input and then our estimated shape, I don't know. If you've ever worked on shape from shading, you'll be impressed. If you work in graphics, you'll probably think it looks rubbish. OK. Again, more comparisons to other state-of-the-art methods. Hopefully, you can see that our reconstructions are a lot more convincing. Now, the really convincing thing is to run this on a video. So there's no temporal smoothness, just running our network per frame, completely uncontrolled. We're using a separate network to remove the sky, if you're wondering why the sky is black. So the main thing to look at here is this shape reconstruction here. The albedo is kind of interesting as well. So this should look like a world with no shading, just the intrinsic color of the objects. And notice as well the lighting estimate is reasonably stable, given there's no smoothing at all here. It's York Minster again, by the way. This is just a tourist video off YouTube. This is Emperor Constantine, I think, statue. OK, and the last thing I want to say on this is a potential application of this is relighting. So you take a photograph and then you edit the lighting and you get a new image. I would say these results are kind of OK. They're not very convincing. I don't think any of you would believe these were photographs. So the work we're doing now, unsurprisingly, involves an adversarial network. So we're trying this idea of adversarial relighting. So the idea is the correct explanation of an image is the one that, when relit, looks realistic. So in other words, we give these to an adversarial network and ask if they're indistinguishable from real images. And then we can propagate that back into the network. Right. I've sort of massively underestimated how long it would take me to get to this point. So I'm just deciding whether or not to cover the second piece of work. Shall I do it quickly? Yeah, OK. OK, so obviously, any questions we will take at the end if we want to come back to the inverse rendering stuff. So The last thing I want to talk about is this recent work on nonlinear shape modeling, so addressing the problems that I mentioned at the beginning. And what we're doing here, which I think is quite neat, is a hybrid between physical and statistical modeling. And it's crazily complicated. This is a sort of medium, high-level explanation of it, and maybe we'll skip over some of it, but if you want details, come and talk to me afterwards. So the model we make use of is called the thin shell model, and this is a model for materials that have non-zero but very small thickness. So it's models that you can materials that you can elastically deform. It's a good model for rubber and things like that, and a reasonable model for skin. Again, paying credit. A lot of the underlying physics and maths for this comes from Cauchy and Green. So the model is actually really neat. We use a discretized version, so we work with meshes, triangular meshes. And what the discrete shell model measures is, if you consider just a pair of triangles, it measures how much elastic energy would be dissipated if you deformed this into this. So it's characterized in two ways. There are two terms. One is the stretching energy, so the in-plane stretching. So you can think of that as changes in triangle edge lengths in your mesh. And then there's the bending energy, and you can think of that as the change in the angle between adjacent triangles. So that's how it's done in the discrete model. OK, so the idea is that this measure of elastic energy can be used like a distance. And there's a lot of rigorous theory showing that this distance measure acts like a distance on a Riemannian manifold. So, or at least locally, if the shapes are close together, it acts like a distance on a nonlinear curved manifold. The really cool thing about it, or what I think is cool, is it's rigid body motion invariant. So if you apply any transformation to this pair of triangles, you won't change the edge lengths or the areas, and you also won't change the angles between the adjacent faces. Okay, so this distance measure between meshes is rigid body motion invariant. Just to show you what this looks like, this is a physical simulation using this model. So in this case, they're applying some forces to it, and then doing a physical simulation of how it deforms. So you get a sense of kind of the materials it's modeling, some kind of rubbery material. There is a parameter that trades off stretching and bending, and then you would get different behavior. You might get more rigid deformations. OK, so some really basic background, but this will lead into something useful. So I'm sure like 90% of the audience are familiar with PCA. So the idea of PCA is it's a dimensionality reduction technique. So let's say you've got people's heights and weights, and you plot them. You would probably notice that there was a relationship between them, and that you could efficiently represent this data using a single dimension. Let's call it size. So the blue points are the best reconstructions of the crosses using only this single axis of size. And this is exactly what PCA gives you. It finds linear subspaces that describe the data well. So a few different ways to think about what PCA is doing. The first principal component that it finds is, well, it's doing two things simultaneously. One is it's maximizing the variance. So when it lines up with the true principal component direction, the spread of the red points is as large as possible. The other thing it's simultaneously doing is minimizing the reconstruction error. So the reconstruction error is the length along these red lines, and you'll see that they're also at a minimum when you align with the first principal component direction. Since I keep mentioning physics, another interpretation is if these were all connected to a rod with a spring, the first principal component direction is also the equilibrium of the spring system. OK, tiny bit of maths, honestly, only on this slide, I think. And most of you will know this, but it's important for what I'm going to do in a second. So to do PCA, classically, you compute the covariance matrix of your data matrix, and so the eigenvectors of this covariance matrix will be your principal component directions. But the problem is this is potentially huge. If your data is very high dimensional, this matrix is like infeasibly big to deal with on a computer. So a trick that you can do instead is, instead of the covariance matrix, you compute the gram matrix. This is like a similarity matrix which tells you how similar each of your training samples is with just a scalar value. If you compute the eigenvectors of this much smaller gram matrix, and then if you pre-multiply by your data matrix X, you'll see that they must be the same thing. So the eigenvectors U of this much smaller matrix end up being, when multiplied by X, the eigenvectors of this much larger covariance matrix. Lots of you may already know this. The reason this is useful is what it tells you is the principal components you want are just a linear combination of the original data, so X is your original data, and these things U that are really cheap to compute give you the weights that you need for that linear combination. Okay, the last thing we need to do before we can get onto our data is that we're not dealing with linear data. We have this nonlinear distance measure, and our data lives on a curved manifold. So there's a generalization of PCA to manifold data. This is called principal geodesic analysis. So in this toy example, imagine you've got some data that lives on a sphere and you want to do something equivalent. Well, you can still compute a mean, which minimizes geodesic distances along this sphere. And you can compute principal geodesics, which are now geodesic curves that, again, capture as much variance as possible. So the way this is actually done in practice is that you construct a tangent plane at the mean, and then you project all of your data in the tangent plane, and then actually you just do PCA. So it's just a linear model again. So we're going to do something similar, but with one proviso. So what we're going to do is learn a statistical model in this space where distance is measured by dissipation of elastic energy. So this will give us some notion of like a physically plausible deformation. The physical model is going to help us interpolate between our samples, but because we're using a distance measure that's rigid body motion invariant, the whole model will be rigid body motion invariant. Okay, last piece of kind of theory stuff, and then we'll see the results. So the problem is that the distance measure we've got only works when your samples are close together. We can't compute exact geodesic distances over the manifold. So imagine you've got some data that lives on a circle. The exact geodesic distance between these 2 points is obviously the path following this green curve. Let's say we only knew how to compute Euclidean distances, but we wanted to compute some kind of approximate geodesic. Well, we can do that. So this would be a path which is discretized with just one sample in the middle. And it's the minimizer of Euclidean distance between these points. And obviously, you can see that if we increase the sampling, we would get a path that gets closer and closer to the true geodesic. So that's basically what we're going to do, but in this much more complicated shell space and using this shell energy distance. So if, for example, I have these two shapes, two hands, two meshes, and then I compute exactly what I just showed you. So I'm going to solve an optimization problem over all the vertices in these three meshes such that the elastic energy dissipated along each step is minimized. I get these really amazing interpolations which do a really good job of predicting what the intermediate shapes look like. So you can kind of, skipping over like a year's worth of me learning differential geometry, you can kind of just do this. So you can do discrete statistics, time discrete statistics. So for computing the average, you're looking for the shape and all of the intermediate shapes along all these paths that collectively minimizes all of the elastic energy required to dissipate, elastic energy dissipated along all of these paths. So it's computationally horrible You have to optimize over all the yellow shapes and the orange shapes just to get the orange shape. Then what this gives us is a local representation of the manifold around the mean, and we know that our distance measure works over small distances, so this is where we do our statistical analysis. I think I'll skip this. There's kind of a trick for how you can do the inner product without requiring... you can do it with only a distance measure. So let's see what these models look like. So these are now nonlinear morphable models, you could call. So this is a cat model. So this is now the second most important mode of variation. The thing to notice is that it's capturing nonlinear variability. And hopefully that all of the shapes look physically plausible. All right, that's a toy example. So we'll see it on some real data. This is human body data, 71 shapes. Obviously, this may not be particularly useful because you're just picking up weird correlations, like in this data, people stick their arms out when they bend their legs and things. But OK, so these are the most important statistically variations in the data. OK, so if we have such a model, we can fit it to data. So this is a real scan of a person that was not included in the training set. And this is reconstructing with our model using increasing numbers of dimensions. I'll show you two applications. So the first is model-based mesh editing. So this is a mesh, and you have some control handles, and you would like to be able to pull them around and get a plausible new shape. The target positions here are really challenging, and the training set has no similar examples in this kind of pose. So these classical methods that are not data-driven and don't have a model just completely fail. This is a state-of-the-art method that uses this data-driven like ours, and this is our result. Hopefully you agree this looks more physically plausible and retains more of the detail. Let's hope these play. OK, so this just gives you a better view of the two edited meshes. OK, and final application is fitting to sparse mocap data. So here what you're given is just noisy marker positions from a mocap system. And in this case, we're using a model that was only trained on 20 scans. So what you're seeing is lots of plausible generalization to new data that comes from the physical model. The result on the left is using a much more complicated model trained on several thousands of scans, and also it has a handcrafted skeleton for bodies. So one final result on an interesting different body shape. So to kind of just sum up what that piece of work is about, maybe in a way that will be relevant to camera, is really it's a way of learning nonlinear blend shapes. So for example, here's another result fitting to some mocap marker data. But our reconstruction is entirely in terms of a very small number of weights that control these blend shapes that were learned from actually a very small training set. OK. So to sum up, I've tried to talk about two recent pieces of work that combine physics-based modeling with some kind of learning. So in the first example, it was deep learning. In the second example, it was statistical learning. The problem of what is the right way to combine model-based knowledge with learning is a really interesting question, I think. And what we're doing at the moment is probably really naive, but it's, I think, a nice direction to go in. So there's still loads of open challenges. One problem in this sort of self-supervised learning is that the signal you get back can be very, very weak. And in particular, if you're really far away from a good solution, it can be completely meaningless, the signal you get back. So for example, people are doing things like learning depth prediction. and their loss function is like cross-projecting one image into the other one. Well, if your cross-projection is nowhere near the correct cross-projection, then the gradient of where that point is ending up is completely meaningless. It doesn't help you solve the problem. So I think there's either a lot of engineering or a lot of clever priors needed to help get it near a good solution to start with. Also, in that particular setup, the model needs to be differentiable, and given that a lot of what we want to do is rendering, I think it's quite important that rasterization is not a differentiable process. So within rendering, you have this discretization, and I don't know the right way to get around that. And then maybe a final thing is, like, as soon as you fix something, it's obviously wrong. So the Lambertian model is a terrible explanation of real-world reflectance. And the thin shell model is a terrible model of human body deformation. So probably a good direction to go in is to make the models partially learnable, or at least, so we keep the components we understand, but where we know they're wrong, we let them also learn from the data. OK, that is my final thought. So thank you very much for listening.
Thanks for that really great talk. Couple of minutes questions?
I've wiped you out, sorry.
So the nonlinear blend chip stuff looks pretty awesome. In terms of the optimization of that, were you doing a similar optimization to kind of a large-scale LOPA PCA style model? Is it, or is it kind of, does it converge quicker? Is it kind of?
It's utterly horrendous. So it's a nonlinear optimization over all of the vertices. I mean, it depends which bit you're talking about, but when you're building the model, it's a nonlinear optimization over the vertices of all of the meshes along all the paths from the mean to the input shapes. Obviously, that's offline. You build the model once. But the fitting is also just ridiculously bad. But there are ways you can speed it up. So you can do things like you can build a linear model, which is over-parameterized, and the correct nonlinear model is like inside it, but some parts